this lecture's topic is manifold learning. We will talk about the manifold hypothesis and about manifold learning with autoencoders. The manifold hypothesis is that in machine learning settings, the data often lies on a low-dimensional manifold inside of a higher dimensional space. Manifold, from the original topological definition, is a space that locally resembles the Euclidean space. So a space that locally has properties as the Euclidean space that we are familiar with. In machine learning, it's often used much looser, the term, and it just means something like a connected set of points that can be approximated well by considering only a small number of dimensions. So in this example here, we see a two-dimensional space, but when we see these training points shown by the blue dots, we could draw this blue line connecting all these dots, and this would mean that all the points lie on this blue line, which is then itself folded or something. But we could see all these points just lying on this line, so they are lying on something one-dimensional, which is embedded in a two-dimensional space. To get a better intuition for the mathematical characterization of a manifold, an important concept is the concept of the tangent planes. And the definition of a tangent plane is the following: at some point x, shown here in the example, on a point of x on a d-dimensional manifold, the tangent plane, shown here by this squared plane, is the plane which is given by the d basis vectors that span the local directions of variation allowed on the manifold. So locally seen for this point here, we can just move in this direction, which are indicated by the plane, and to stay at the manifold. If we would move, for example, in that direction, we would move away from the manifold, and if we move in this direction as well, right? But if we move somewhere on this plane, we are very locally moving in a direction that stays on the manifold. And this is also what is meant when we say locally the manifold resembles an Euclidean space, because this tangent plane has like Euclidean properties, and very locally it's matching the surface of the manifold. So to repeat, the manifold hypothesis is that in machine learning settings or in general data settings, often the data of interest lies on a lower dimensional manifold, which is embedded in a higher dimensional space. And this, of course, must not need to be true, but in the general data that we get in the artificial intelligence context, like images, sound, or text, it seems to be at least approximately correct. And the arguments for that are that if we think about probability distributions over images or texts, it seems like that all the data is highly concentrated. To make this clear, if we have an image with n times n pixels, then the space is n times n dimensional. If we would just sample from these randomly, from this space, from this n times n dimensional space, it's very unlikely that just by coincidence we would get something that really looks like an image, like something that we could interpret or recognize. Probably it would look like random noise for us. And the same argument for text. If we would just sample letters randomly, which then it's very unlikely that what comes out is a meaningful sentence. So this says that a lot of points that we could have in the space does not really belong to the space of the data that we really observe. So the data seems to be concentrated, we don't use all the space which is there in this high dimensional space. And second, the samples are connected to each other by other samples. And each sample is surrounded by other highly similar samples that can be reached by transformation. This is very clear for images. If we have an image which shows something meaningful, we also slightly changed image in the neighborhood is an image of something meaningful. For example, we could just dim the light a bit and we would still recognize the same thing on the image. Or we could rotate the object a little. So these are images which are close by in the image space. Because we just move a little bit and still they are belonging to the space of meaningful images. So the data is somehow connected and not arbitrarily distributed in the space. So these are two arguments that intuitively make clear that we can assume that something like the manifold hypothesis holds in typical data we use in machine learning. When we train an autoencoder, we can think about it as learning the coordinates of this manifold, because we have two compromising forces. At once, we want to learn the representation Z, so that we can approximately reconstruct X by the decoder. And secondly, we have some force that we want to satisfy some architectural constraints or regularization properties. So together, we force the hidden units to capture information about the structure of the data generating distribution without copying all the information. So the autoencoder can only afford to represent these variations which are needed to reconstruct the training examples. So if the data generated distribution concentrates on a low dimensional manifold, the representations that are learned by the autoencoder might implicitly capture exactly these local coordinates of the manifold, which are given by the tangent plane. So this factors of variation which describe how the data varies on the manifold. And here we see a small experiment, or the results of a small experiment illustrating the manifold property. There was data which was produced by shifting or translating 9 from the MNIST data set from top to bottom. So these images are the same image but translated. And then the data produced by that is projected with PCA to a two-dimensional space, and shown here. So we see that the data produced by that lies on a one-dimensional manifold, shown by the blue line. And there's only one direction of variation, because it's the same picture and just shifted. And so in such a one-dimensional manifold, we just have a tangent, which is giving the tangent plane, and we can also see when moving in direction of the tangent what changes the image. This is shown here, and gray are the pixels which don't change. It makes sense because there is a background, and black are the pixels which are white and become black when moving, and white are those which become white were black before. So we see here's a downwards movement. So the tangent shows in the direction where we can observe the factor of variation in this one-dimensional manifold. In general, there are different or in manifold learning, we usually want to learn an embedding or a representation of the points on the manifold, which are lower dimensional. And in general, there are different approaches to that. There are, on one hand, non-parametric models, which learn an embedding for each training example, or approaches like the autoencoder, which learn more general mapping for any point in the input space, because after learning it, we could apply the autoencoder to new data points and get mapping for those new points as well. And since the displaces or problems used in artificial intelligence can have very complicated structures, and so it may be difficult to capture the local interpolation, this motivates the use of deep learning or the distributed representations learning that deep learning enables us to do, since deep learning, as we know, is very good in extracting features and projecting data from complicated in easier feature spaces, which give us a distributed representation.